work a little better on this laptop. I'll have to see if this works out. Hope we can get this up. Make sure my microphone's working. All right, let's try that. It's not going to focus on me here, is it? All right, well, I hope this will come out in a second. Just wanted to remind you we had last time the cross product. Let me put this up at the top. I wrote up part of this in advance. The Zoom thing isn't sitting on me again, is it? Let's see. I cannot get this to show me. Online, are you able to see me? I don't know if you can take the mute off for a second. There we go. Maybe they're in. Okay.
I can see you. Yes, sir.
Okay. Thank you. So today I'll try this from the laptop, see if this is more readable. I can put it more straight on here. And I could the camera that's in here. Let's see. Move it back just a little. There's the cross product. I'm missing the bottom of the board. Maybe I can just try and be careful of that. So the cross product, we defined it this way, and we said we can compute V cross W only in 3 dimensions. For vectors with 3 components, we define it to be the vector. The cross product of vectors is a vector, unlike the dot product of vectors was a number. And it's defined to be, in terms of the components of V and W, V2W3 minus V3W2 for the first component, V3W1 minus V1W3 for the second component, and V1W2 minus V2W1 for the third component. And it's hard to remember that, but if you do this 1, 2, 3 rule, you think first component uses 2 and 3 minus its reverse. Second component uses 3 and 1 minus its reverse. Third component uses 1 and 2 minus its reverse. It's just cyclically 1, 2, 3, 2, 3, 1, 3, 1, 2. It's pretty easy to do that, and I find this is faster than the second definition. But if this isn't easy enough to remember, what's even easier to remember is that you can put these into a determinant if you've seen determinants before. If you haven't, then you need to learn them because we're going to use them here later in the semester anyway. And so a 3 by 3 determinant will tell you how to compute the cross product only. You get this also, you get the same result. You load the elementary vectors along the axes, I, J, and K into the first row. Then you load the components of vector V in the second row and W in the third row. That's how everybody can easily remember it when they get out of the class. When you've seen determinants before in linear algebra, or maybe somewhere else, and again, we'll use them again later in this text. Tell me if I'm blocking over there, I'm sorry. And now how do you compute a 3 by 3 determinant? It's actually defined in terms of 2 by 2 determinants. What you do is you take the element in the first row, first column here, and multiply it by the determinant got by wiping out its row and column. So it's this one here. Right? So there it is. And then you take minus this one in the second position here, wipe out its row and column, and you've got these 4 numbers left, and you take that determinant. And then you take plus the third component of the first row, that's K, and wipe out its row and column, and now you've got this matrix left over here. And so you take I times the determinant gotten by wiping out the row and column of I, minus J times the determinant gotten by wiping out its row and column, plus K times the determinant gotten by wiping out its row and column. And this is how the 3 by 3 determinant is determined. It's defined that way. And then 2 by 2 determinants, how are they defined? Well, there's just the difference of the products of the diagonal. For a 2 by 2 determinant, it's defined to be the number that you get by taking this times this minus this times this. So diagonal minus diagonal. V2 V W3 minus W2 V3. computes the determinant of this matrix here. And so when you're all done computing V2W3 minus W2V3, V1W3 minus W1V3, and this one times this one minus this one times this one, you look at this and say, oh, that's the same thing we defined up there. So that proves that this determinant formula actually computes what we defined the cross product to be. All right. And now there's an interesting thing that happens when you do that. The first theorem regarding the cross product is the following. The cross product V cross W is actually orthogonal to both V and W. And what's more, they're orthogonal by the right-hand rule. What's the right-hand rule? It's like this. If I take a vector V in three-dimensional space here, and a vector W, so you have to imagine this with axes around it or something, maybe here's over here, X, Y, and Z, so it's in three-dimensional space. And you take V cross W, the idea is if you take your right hand and put it in the direction of V, and you turn your right hand, your wrist towards W, then the cross product points in the direction your thumb is pointing, your right thumb is pointing. If you use your left hand and turn that way, your thumb would point down here, but the right hand points in this direction. And so you take V cross W must point in this direction, like that, perpendicular to both of these. It can be the zero vector because remember the zero vector is considered to be orthogonal to every vector. So here might be V cross W. We haven't talked about its length yet. And that shows you something interesting, that actually our coordinate system is right-handed. If you take the little vector I along the x-axis and the little vector j, the unit vector along the y-axis, and take their cross product, I cross j, you go in the k direction, right? So we call our coordinate system, the way we plot it here, I, j, k, and almost everybody makes sketches in three dimensions using a right-handed coordinate system. If you were to do left-handed, then the z-axis would have to go down, and there's actually a difference between the two. In real life, people in biology, they find out that all life form is based on a left-handed amino acid somehow. There aren't any right-handed ones. Why is that? It's a big curiosity, but there is actually an important distinction between left and right-handedness. And the only place I've ever seen left-handed coordinate systems used is in Russian aircraft, and I think they want their, the x-axis out of the nose and the y-axis out of the wing, and they want the z-axis to point maybe down instead of up or something. I don't know, but hardly anybody uses those. So we'll use right-handed x, y, z all the time for plotting. And as you can see from the cross product, that's actually important because the cross product goes by the right-hand rule. You want to point it the right direction. Now we can do a partial proof. I'll prove that they're orthogonal. I won't prove the right-hand rule, and I'll actually only do the first part of the proof, but the second part is easy. Partial proof, if I take V dot V cross W, the claim is that V cross W is perpendicular to V. Right? That was the first part of the proof. So perpendicular orthogonal means that the dot product is zero. So I have to show that this is zero. I'll show that V is orthogonal to these. Then you can do an exactly analogous proof to show that W is orthogonal also. And then I'll leave out the right-hand rule part. This is V1, V2, V3 dot, if I write out all the components from the original definition, V2, W3 minus V3, W2, V3, W1 minus V1, W3, V1W2 minus V2W1. And I take that dot product, I take V1 times this first component here, V2W3 minus V3W2, and then plus V, right? This times the first component times first, second times second, plus third times third is the dot product. So I'll take V2 times the second component of the cross product, V3W1 minus V1W3, and then plus V3, third component here, times third component here, V1W2 minus V2W1. And now you notice that these things all cancel out. V1, V2W3 here cancels with, let's see, minus V1, V2W3 here. So that one cancels that one. And V1, V3W2, this one, cancels over here. Let's see. V1, did I get that right? Yeah, V3, V1W2, this one. And similarly, this one and this one cancel, and you wind up with 0. Yes, they are orthogonal. And then you take W with this thing, you can show W dot V cross W, you can also show that's equal to 0, showing that it's orthogonal to both. So this is kind of nice when you want to get a vector that's perpendicular to two given vectors. That happens in lots of applications. Like you've got a rotating coordinate system for your spaceship or something, and you want to put one vector through the nose and one vector out the right wing or something. You can take the cross product to get the other third direction perpendicular to it. There's lots of applications like that. All right, so that's one nice application. Oh, by the way, I should mention also, a lot of books prefer, instead of using the right wrist, to use your 3 fingers on your right hand. If you put your thumb in the direction of V, this keeps you from having to raise your hand in class also. This is a good idea. Maybe you don't have a question. The thumb in the direction of V, the second finger in the direction of W, then your middle finger points in the direction of V cross W if you use your right hand, but if you use your left hand, it's the wrong direction. So you can use your fingers instead of your hand if you prefer. I see math books use that a lot. Physicists like to use the right wrist thing a lot. You can use whichever one you like, whichever one you like. All right. Now let's do a computation with that. We got to do an example, right? Here's an example then. Suppose I were to take 1 minus 3, 2, and cross product that with 4 minus 2 minus 1. What's that cross product? Well, I can compute I, J, K in the first row, this vector in the second one, 1 minus 3, 2, and this vector in the third, 4 minus 2 minus 1, right? And so now I'll take I, wipe out its row and column, right? And I'm left with this matrix here, its determinant, minus 3, 2, minus 2, minus 1. And then minus J, the second element here in the first row, wipe out its row and column. That means leaves me with the 1, 4, and the 2 minus 1, right? I wipe out this stuff and this stuff. And there's what's left. And then plus K, wipe out its row and column. I'm left with this matrix and its determinant, 1 minus 3, 4 minus 2. Looks like that. So let's see, I've got I times minus 3 times minus 1. All right, because for a 2 by 2 determinant, you take diagonal product minus diagonal product. So minus a minus 2 times 2, and then minus J, and I'll multiply by 1 minus 1, minus 4 times 2, and then plus K times 1 times minus 2, minus 4 times minus 3. Let's see, we've got I times 3 plus 4 is 7. Minus J times minus 1 minus 8 is minus 9. And then plus k times minus 2 plus 12 is 10. It looks like 7i plus 9j plus 10k. That was pretty complicated. Do I think that's right? How do I check if that's right or not? Maybe it's wrong. I made so many computations. If it's really right, then it should be perpendicular to both those vectors I put in, right? So I can take the dot product actually in my head and do a check, right? I can do this in my head, but I'll do it on the paper just to show you. If this is really perpendicular, then the two vectors whose cross product I took need to both be orthogonal, have dot product with this one 0. So take the first vector of the cross product, 1 minus 3, 2, dot it with this vector, 7, 9, 10 that I just computed. That should be 0 if I didn't make a mistake. We better check here. This looks crazy, right? 1 times 7 plus minus 3 times 9 plus 2 times 10. 7 minus 27 is minus 20 plus 20 is 0, sure enough. And if I want, I can check the other one. If I take the other vector 4 minus 2 minus 1 and dot product that with my cross product 7, 9, 10, I should also get 0. Let's see, I get 4 times 7, but you can often do this in your head. Plus minus 2 times 9 plus minus 1 times 10. Nothing nicer in a test than being able to check your answers, right? So showing you a way to help check your answers. 28 minus 18 is 10, minus 10 is 0. Sure enough, it's orthogonal, both the vectors. It doesn't show it has the right length, but boy, if it's perpendicular to both of those, it's probably right, right? So there's a check that you can do on your cross product to see if maybe you made a mistake. Any questions on all that? That's what you guys need to do for the guys and people online here. Ask questions. Although maybe they can respond if they take the mute off. All right, so there's an example of computing a cross product and checking it. We haven't talked about its length, however. Maybe the length is of significance, right? What about the length of the cross product? This one we won't prove because it's too long. But this is a very important theorem for these. Just like the dot product has great significance geometrically, this is why the cross product has great significance geometrically. For any cross product, the length of the cross product, right, the direction is significant because it's perpendicular to the input vectors, but the length of the cross product is length of V, length of W, sine of theta, where theta equals the angle between them, between 0 and 180 degrees, or 0 and pi radians, just the same angle we did for the dot product. All right. Draw it like this. Doesn't matter how you arrange them, right? You take in whatever number of dimensions. The smaller of the two angles, not this big angle over here, the one that's between 0 and 180 degrees, and call it positive measure, no matter which way you turn from W towards V or V towards W. And that's the angle between them, theta. So that's a nice theorem that we don't have time to prove. But it says something of great significance. It now has applications like this. This one is not used as much because there's another nice way to do it too, but I just want to point this out, is it complements the dot product, right? The sine and cosine kind of complement each other. Here's an interesting picture. Suppose I was to take this projection thing again. Here's what I've got. And I'm going to take the vector V and project it onto W. And so you take the light source at infinity and drop it down. And we call this thing the projection of V onto W, or the component of V parallel to W. And we call this one the component of V perpendicular to W, right? And those were significant when you wanted to break up force vectors and velocity vectors and things like that. And so you want to know their length. What is the length of this one here? Well, if theta is the angle between them, between V and W, then you recognize from trigonometry that this side here has to have length, which is what? Well, it's length of V times the cosine of the angle between the two vectors, right? Why is that? It's so that this side over this side is the cosine of theta, right? This over this one is length. Since this is a vector V, it's length. It's the length of V. And so you take hypotenuse. This side is the hypotenuse times the cosine theta. And this one over here has length, which is length of the sine of the angle between them, right? So that this over this is the sine of theta. Now, what is that in terms of the dot and cross product? This is just, well, length of V, length of W, cosine of the angle between them was the dot product. So I could say this is actually V dot W over length of W, right? Because V dot W is length of V, length of W here, excuse me. Length of V, length of W, cosine of the angle between. If I divide that by W, I get this, right? This one over here is the length of the cross product. The length of the cross product divided by W. So the dot product divided by W, and actually technically I should say, this length is the absolute value of V cross W, right? V dot W gives you the component here, which can be negative if theta is bigger than 90 degrees. So I'll say the length is the absolute value. But the absolute value of the dot product over length of W gives you the one side of the triangle. The length of the cross product divided by the length of W, this is the W down here, that looks like it, it looks like a V, gives you the other side of the triangle. So they complement each other in that nice way geometrically, which is one interesting thing, but we don't use it as much because we always take the projection and then subtract this one minus the projection to get this one. But it does sometimes have that application. Here's a more important application. 2 is the area of a parallelogram. Designed from edges that are vectors, right? V, W. If they're both vectors at the same point P, then they determine a unique parallelogram as follows, right? Suppose I take any point P whatsoever in 3 dimensions, and I have a vector V coming out, and I have a vector W coming out from P. That determines a unique parallelogram by putting the vectors end to end, right? I parallel transport W and put it over here, get a vector equivalent to W. And then I parallel transport V and put it over at the end of W, and I get a vector equivalent to V here. And this is the parallelogram I'm speaking of. We might say, what is its area? A. All right. Well, there's a neat way to compute this. I wrote this up. And here it is. Here's the derivation. If I want to find this area of parallelogram, this is where you use a little intuition here and say, I don't know what that is. How do I find it? You can drop a perpendicular down here from the end of W, say down to V, and look at this triangle, and you recognize if you took this triangle out and moved it around over here and put the triangle here, then you observe that the area of the parallelogram is the same as the area of this rectangle, all right? And I know the area of a rectangle is just base times height, but the base of the rectangle here is the same as the top of the rectangle here is the length of V. So the base of the rectangle is the same as this, is length of V. And what's the height? The height here Well, again, from trigonometry, it's the length of a hypotenuse times the sine of the angle is this leg. And so the height here is this one here also, is linked to W sine of theta, where theta is the angle between the two vectors. So the area of the parallelogram, A, is also the area of this rectangle, which is base length of V times height length of W sine theta. Maybe there's some parentheses around that, just to make it clear. But by our last theorem, length of V length of W sine of the angle between them is the length of V cross W. And so the length of V cross W, this is a theorem we just proved, gives you the area of the parallelogram determined by the two vectors put at a single point. How about that for a nice theorem? It does a nice geometry result, computes the area of a parallelogram. This is actually of use if you have coordinate systems where the two axes aren't perpendicular, right? We've been doing areas under a curve by adding up areas of rectangles. What if the x and y axes aren't perpendicular, they're angles? Looking at up areas of parallelograms, and actually this cross product then has some uses in computing areas in non-orthogonal coordinate systems. We won't do that here, but I'll just make that interesting point. You can do abstract mathematics with it. And I said that the great Gauss said, in Prince of Mathematics, they called him, he put his picture in the 20th century for a while on some of the Deutschmark. I forget how many, what number it was, but they put his picture on there. So great. He said we must always seek to generalize, right? So you always want to generalize these things in abstract. All right. So let's use that now to actually compute the area of a parallelogram, or more significantly even, if you have any polygon or in the plane, you can triangulate it, break it up into a bunch of triangles to find its area. So what's even more significant is finding the area of a triangle. Suppose I want to find the area of a triangle, I might recognize that the area of any triangle, maybe I want this one, is just half the area of the corresponding parallelogram, where I take this triangle and flip it over and turn it around here, right? And flip it over the other way and twist it around. These are two congruent triangles just flipped over. And so the area of a triangle is actually half the parallelogram thing. So if I want to compute the area of a triangle, say with these three vertices, how can I do it? I find the area of the parallelogram and just multiply it by half, right? So there's a nice formula actually from the cross product from finding the area of a triangle, and therefore you can find areas of polygons nicely like this in multidimensional space by triangulating it. Maybe that's not quite the right word, but breaking up into a bunch of triangles and finding the areas of the triangle. So suppose we have these 3 points, and let me cover this up for the moment. And suppose I want to find the area of the triangle that's determined by those 3 vertices of the triangle, right? In 3-dimensional space. In 2-dimensional space, you can sort of figure it out, but at last, how do you figure out the area of a triangle? Take 3 arbitrary points in 3 space. It's very easy using the cross product. This is just what you need to do it quickly, right? All you have to do is think of making, if you have, say these are the 3 points of the triangle, you just compute the vector v from one point to the next, compute the vector w from the first point to the third one, and then 1/2 the cross product gives the area of this little triangle, right? Because the cross product gives the area of the parallelogram, and the triangle is half that. So let me do just that. V can be the vector from this one to this one. I subtract the coordinates, 6 minus 1, 9 minus 1, 0 minus 0, right? And I get this vector 5, 8, 0. Then I'll take W from the first point to the last point, right? And subtract the coordinates. 1 minus 1, right? 4 minus 4 minus 1, and 8 minus 0 is 0 minus 5, 8. And so I have these 2 vectors, 5, 8, 0, and 0 minus 5, 8, are the vectors here and here, going along 2 edges of the triangle. Now I can find the area just by taking 1/2 the length of the cross product. So I'll say the area of the triangle area, that's my little triangle area, is 1/2 the parallelogram area, that's what that says, is 1/2 the length of the cross product, right? So now I need to compute my cross product. So we can use the determinant formula again, and the idea is I'll take the length, that's the double bars. So by the way, this is also called the norm of a vector. So the length, norm, or magnitude of a vector all mean the same thing. It just means root sum square of the components in Euclidean space. And other exotic spaces, they do other strange things. But, so if length or magnitude or norm of the vector all mean the same thing for us in Euclidean space. So we'll take V cross W, taking I, J, K, and here's V, the first vector, right? 5, 8, 0, and here's W, the last one, 0, minus 5, 8. And so I need to take 1/2 the length of this vector. And once again, I'll need to compute it by the determinant formula here. I wipe out 5 row and column, and I get 8, 0, minus 5, 8. That's what multiplies I. And then I take minus J, and I wipe out this row and column, and 5, 0, 0, 8 goes in here, and wipe out the row and column with K, and this matrix goes in here. By the way, this extends to higher dimensional determinants too. We defined our 3 by 3 determinant in terms of 3 2 by 2 determinants. If you ever need a 4 by 4 determinant, and you're working in 4-dimensional space or something like that, space-time, then you can compute that in terms of 3 by 4, 3 by 3 determinants. In 5-dimensional space, it's 5 4 by 4 determinants to compute the determinant. As you can see, that becomes very cumbersome. Actually, if you try and do a 70 by 70 matrix, it takes you more than 10 to the 100th multiplies to compute the determinant in this manner. This is not an efficient form. You don't want to do it for bigger than 4 by 4 cases, but 10 to the 100th is a Google, right? That's where it's not spelled like the one online, G-O-O-G-O-L. The guys who started Google couldn't spell, I guess, but anyway, but it's such a big number that if you had a computer for every atom in the world and working at current technology speeds since the beginning, since the creation of the universe, you still would not have had time to compute a 70 by 70 determinant with modern computing skills. It's such a long process. So I mean, it's not long before this becomes absolutely unwieldy for large determinants, but it works for 3 by 3s and 2 by 2s and 4 by 4s. And here's how you compute it, right? The determinant of this one is 8 times 8 minus this times this is 64 times I. And then this one is 5 times 8 minus 0 times 0 is 40 times minus J. And then minus 25 minus 0 times K. And let's see what we get here. There it is. It's the length of this vector. Well, how do you take the length of a vector? You root sum squared its component. Square root of 64 squared plus minus 40 squared plus minus 25 squared, right? And then multiply it all by 1/2 because you want the triangle area, not the parallelogram area. And you wind up with 7 square root 129 over 2. So there's the area of that triangle computed pretty quickly with a cross product. So there's the application of its length. Right, its direction is orthogonal to the 2 input vectors. Its length is the area of the parallelogram it determines. How about that? So this is a long section. It has all sorts of stuff. Here's the triple product, or the scalar triple product. Maybe I should call it. The idea being that a scalar is a number. It comes out to be a number when you put these 3 things together. This comes up often enough, they give it its own notation. If you put 3 of these in braces, or they may have put it vertically in the book, I don't remember. There's different notations, because it's not used that much. But UVW in parentheses mean take U dot, that's not a minus, that looks kind of funny, doesn't it? U dot V cross W. You can leave these parentheses out, right? You can only do this in one order. You can't do U dot V cross W because U dot V is a number. You can't cross product it, right? It's not a vector. So you can leave these parentheses off. But U dot V cross W is the way we define the scalar triple product. And it comes out to be a number, right? And it has significance too, right? If you take V cross W, that's a vector. You dot product with another vector, you get a number, right? A scalar, we call it. And so this number has the following significance. Suppose you take the three vectors u, v, w, and those determine in free space a unique parallelepiped. Anybody know what a parallelepiped is? It's this thing here. It's a six-sided figure with parallelogram sides. They're all parallel. Opposite sides are parallel. So when you take the three vectors and put them at a single point P, here's u maybe, and here's v, and here's w. You take a copy of v and put it over here, and a copy of w over here, and you make a parallelogram like we did before from two vectors. You make a parallelogram from these two vectors, you make a parallelogram from these two vectors, and then you fit three more sides opposite, and you construct this six-sided figure with parallelograms on all sides. A rectangular box is a special case of this, where these are all 90-degree angles between them, right? So you can impress your friends with your mathematical knowledge right next time you mail a package. Here's my rectangular parallelepiped that I had for Minnesota or whatever. I wonder what you're talking about, but anyway, so suppose we want a volume of a rectangular parallelepiped. How can we find that? It turns out we can use this scalar triple product as follows, because, let me move this up a little bit. What is the volume of this thing? Well, this is how you compute the volume of a solid. That's done by extruding it, where you take the parallelogram base and you just slide it along this way. The volume of any solid constructed in that fashion is just the area of the base times the height. So if you slide it perpendicular to the base in this direction, you just need to know the height of the thing. Well, what's the height of this thing? If you call this the vector u, you can construct this right triangle. And this length here, again, is the length of the hypotenuse times the cosine of this angle, right? By trigonometry. This side is length of u, cosine of theta, where theta is the angle between this vector and the base. But this vector being perpendicular to base is in the direction of the cross product v cross w. And so this is the angle between v cross w and u. And so what you have is the height is the length of u times the cosine of the angle between v cross w and u. So it's kind of complicated. Now what's the area of the base? Well, that's a parallelogram, so the area of the base is the length of v cross w. And now what you have is that the volume of the box V, the rectangular parallelepiped V, is, I'm going to go to the other page, it's the base times the height, but the base was length of V cross W. The height was length of U cosine theta. And now you recognize the length of the vector cosine of the angle between them. That's just the length of that's just the dot product, right? Length, cosine of theta. So this is, and I should put absolute value on here because you want the height to be positive. So to get positive height, you take length of V cross W, length of V, absolute value of cosine theta. And so what you have is absolute value of V cross W dot U because length, cosine is the dot product. But now you can, the dot product is commutative. You can take the dot product in the other order. And now, that's a triple scalar product. U dot V cross W. You can write it like this. And I should put absolute value on here. And that's the theorem, is the volume of the parallelepiped formed by three rays emanating from a point UVW at a point P is the absolute value of the triple scalar